When you get astronomers talking, it's very rare that the words spectra, spectroscopy or spectrograph will not appear. This is not a surprise. The spectroscopy is one of the sharpest tools in an astronomer's toolbox when he is looking at the mysteries of the universe. Before we can talk about spectroscopy, we first have to look at light as a whole. The light that we detect with our eyes comes from our nearest star, which is the Sun. The light we see with our eyes travels the 93 million miles from the Sun to the Earth in 8 minutes and 20 seconds. The light arrives to us in little parcels of energy called photons. Now these photons all have varying energy values, and this decides their wavelength. And that's all I'm going to say on photons. If you want to research them more, then you can do at a later date. For now, all we need is that the energy contained in the photon decides its wavelength. Remember that for later. Right, the full range of light is huge, and as I said, the wavelengths vary a lot. Here is the spectrum of all light, and as you can see, it goes from very low energy waves, which are radio waves, all the way up to the high energy waves, which are gamma rays. For today's purpose, we're going to be looking at the visual light. As you can see, the visual light sits on the spectrum, which is known as the electromagnetic spectrum, just above halfway. It covers a very small part of the spectrum. As I said, the photons are little packets of energy, and they vary. And we can see this by using a very simple experiment, an experiment that you've probably did at school. And that is using a source of light and a triangular prism. If you pass the light through one side of the prism, it gets bounced around 2 or 3 times inside the prism due to the angle of the actual facets, and then it reappears the other side of the prism, and you can project it onto a screen. Now as you can see, you will find a lovely rainbow effect, which stretches on one side from red to the other side, which is blue / ultraviolet. This is showing you the different values of energy in each of the photons. We can test this theory by placing the sensor of a thermometer in the red light, and it will read a temperature. If you then move the sensor to the blue or ultraviolet light, you will see that the temperature is actually higher, because the photons at that end of the spectrum are carrying a higher energy, whereas in the red it's a lower energy, hence the lower temperature. By performing this experiment, you are in good company. Isaac Newton himself used to use this system to split the light into its constituent parts. So a quick recap so far. The low energy photons with long wavelengths sit at the red end of the visual light spectrum, whereas the high energy photons sit at the blue end with their shorter wavelengths, and all the wavelengths in between give us the different colours of the rainbow. Also, visual light is only a very small part of the whole of the electromagnetic spectrum and sits halfway along. So, back to our original questions. First, what is a spectrograph? A spectrograph is an instrument that separates the light from a star or any other light source into its constituent colours or wavelengths. So it's a bit like the prism we mentioned in the experiment earlier, but gives us the spectrum in a far greater detail. Question 2. What is spectroscopy? Stellar spectroscopy is the analysis of the lines in the spectra of stars and is by far an astronomer's most important tool for investigating the physical nature of stars. So a spectrograph will give us the spectra of a star, but in far greater detail, in the form of little lines. And the study of these lines in the spectrum will tell us a lot about the star and its environment. So what can we see in this extra detail? We can see the radial velocities of stars, that is, motion of the star towards or away from Earth. We can calculate relative masses, orbital periods, and orbit sizes of stars in a binary system. We can measure temperatures, atmospheric densities, and surface gravities of stars. Also deduce magnetic fields and their strengths on stars. We can glean the chemical composition of stars, what atoms are present and in what states they exist. We can also watch the sunspot cycles, or should we call that star spot cycles. In that list I mentioned surface gravities of stars and also magnetic fields and their strengths on stars. Well, I'm not going to go into these because I consider this more advanced spectroscopy, and you have to use methods like the Zeeman effects and the Stark effects, so we'll leave that for another day. So back to these lines in the spectrum that give us all this information. The lines we see in the spectrum appear either dark or very bright. The dark lines are called absorption lines, while the bright lines are called emission lines. For our purposes, and to make it easier for me, I'm just going to talk about the dark lines that we see, the absorption lines. So, what are absorption lines, and how do they get there? Well, to explain this, I must rewind the clock on the life cycle of the photon. The photon is first produced in the centre of the Sun, and it spends probably the next 100,000 years trying to escape the Sun. But in the centre of the Sun there is so many high energy particles that it's being buffeted around, ricocheted, ping-ponged all over the place. But eventually, if it's lucky enough, it will reach the outer layers of the Sun. Now in the outer layers of the Sun are all the elements that the Sun is producing, and also the elements that were present in the star's maternal gas cloud that gave birth to it. Remember I said each photon carries an energy level, which in turn determines its wavelength. Different energy levels, different wavelengths. Now the elements in the outer layers of the Sun are in a state we call ionized. This is where when an element is exposed to high energy levels and heat, the energy levels and the heat will actually start to strip away electrons from the atom. For example, let's have a look at iron atoms. If an iron atom is in an ionized state, it will carry an energy. So again, it will have its own wavelength. Now, the photon, which is running the gauntlet of all these elements in their ionized states, if it happens to meet an ionized iron atom, which has the same wavelength as the photon, then the photon will be absorbed. And all the other ionized iron atoms with the same wavelength will also be absorbing all the photons with the same wavelength. This results in a deficiency of photons at that specific wavelength actually leaving the Sun's surface. This means when we project the spectrum onto a screen, you will see lines where the photons that have been absorbed are missing from the spectrum, and hence you get your absorption lines. And this tells us that iron at that specific ionized state exists in the Sun's outer layers. On this slide you can see the absorption lines for different elements. But we can also take this one step further. Let's get back to our iron atom. If the iron atom is exposed to higher energy levels and larger heat temperatures, then more of its electrons will be stripped. With the loss of each electron, it will exist in a different state. These ionized states of the iron will be betrayed in the spectral line also. They will be producing their own absorption lines. So what is this telling us? Not only is it telling us that iron is existing in the outer layers of the Sun, but also it is existing in several ionized states. We can see this in the spectral lines. So that also means that the outer layers of the Sun are at different temperatures in different areas, so that these ionized iron states can exist. If the Sun's outer layers were all one uniform temperature, we would only see one ionized state of iron. So the temperature varies over the surface. Job's a good un. There is a way we can test this. If we go back to the prism experiment we talked about earlier, But this time, between the light source and the prism itself, if we place a test tube full of hydrogen and then pass the light through the test tube, then the prism, and project the spectrum onto a screen, you will actually see in the spectrum definite black lines. This is the spectral fingerprint of hydrogen. These element fingerprints in the spectra of the stars tells us so much about the star and its environment and where it actually came from. But I also mentioned that we can actually detect movement by again looking at the absorption lines in the spectra. We do this by using a method which is the light equivalent of the Doppler shift. Now the Doppler shift we've all experienced. It's when an emergency vehicle is coming towards you with its siren going. As it moves towards you, the pitch gets higher and higher. But as soon as it passes you, the pitch gets lower and lower. This is because as the vehicle comes towards you, the sound waves are actually compressed, increasing their frequency. But as it passes you, the sound waves become stretched, giving them a lower frequency, so the tone drops. Well, light acts in exactly the same way. If a bright object is moving towards you, the light waves actually get squeezed, increasing their frequency, which means the whole shift is towards the blue. If an object is moving away from us, the light waves actually get stretched, and the spectrum moves towards the red. This is called the red/blue shift, and it tells us which direction an object is moving, away or towards us. So what do I mean about red shift and blue shift? It means that when we look at the absorption lines in the spectra, if an object is moving towards us, the whole of the absorption lines will move towards the blue end of the spectrum. If it is moving away from us, the absorption lines will slip towards the red, and this indicates which direction it is moving in comparison to us. But this can be taken one step further. We can also, using exactly the same technique of the red shift and the blue shift, detect small wobbles in the stars themselves. Also, it will tell us if a star has a companion, and by watching their separate orbits, by using the red and blue shift, we can determine their size, their orbital lengths, and their masses. And all this can be discerned from the red and blue shift of the stars. Sunspots will be betrayed by the effects they have on the surface of the star themselves, and by looking at the elements and the states of ionization they are existing in. Also, spectroscopy can be turned towards nebulae and galaxies, again looking at the interstellar medium between all the stars, telling us how old the galaxy and all the elements that exist within the interstellar medium. And all this just from looking at a few black lines on a spectrum of a star. Well, I hope this makes it a little bit simpler for you if you didn't know anything about spectra. And keep an eye out for more of these jargon busters. Hopefully there'll be a few more on their way. Remember, you will find us on Monday nights at 8 PM UK time. Come and join the panel, and if you have any questions, drop them in the chat and we'll answer what we can. So I hope to see you soon there. Just before you go, just one more amazing wow fact. Now, we all know the universe started with the Big Bang, and not long after the Big Bang, in cosmological times, the universe cooled enough to actually form the first atoms. The first elements formed were hydrogen at 73%, followed by helium at 25%, and a tiny splattering of other elements. This hydrogen produced so early in the universe's history is all the hydrogen it is ever going to have. No more will ever be made. Now, our bodies are made up between 55 and 75% water. Now, water is 2 hydrogen atoms connected to 1 oxygen atom. So just think about it. The atoms that are going to make up your body, some of them are almost as old as the universe itself. Isn't that amazing? It's a bit of a wow factor, that. Anyway, we'll hope to see you Monday nights. Everybody please take care, and I'll speak to you soon. Bye for now.
Okay, now let's talk about the other announcement, which came an hour later. So we had to rally around and get things organized to cover them both. The Milky Way in neutrinos. What you are looking at is IceCube. This is an observatory at Amundsen Station at the South Pole in the middle of the Antarctic continent. Now, it doesn't look like a conventional observatory because where are the telescopes? Well, it doesn't have any telescopes. It actually doesn't look upwards at all. It looks downwards. What is this all about? So if you look at top left of this graphic, there's the laboratory sitting on the surface of the ice. And underneath the ice, they have dropped 86 strings, if you like, cables, with a total of 5,160 optical sensors. What on earth is this all about? And they go down a long way as well. You can see on the right the height compared to the Eiffel Tower. Now, they're there to detect neutrinos. These ghostly particles, which are very mysterious, coming from the depths of space. They're very difficult to detect because neutrinos pass through matter as if it just weren't there. It's often said that a single neutrino could pass through a sheet of lead 30 light years thick and not even notice it. So they are very difficult to detect because they don't interact with ordinary matter. But occasionally they do. And this immense detector, the IceCube laboratory at the South Pole, which was built over quite a few years, because as you can imagine, drilling all those holes that far down in the ice, 2,820 meters down in the ice, and lowering all those 5,000 odd detectors was a huge job. When a neutrino passes through the ice, occasionally it does collide with an atom, and that produces a very faint flash of blue light called Cherenkov radiation. And this, as you can see on the left, these DOMs, these digital optical modules, these are basically light detectors that can detect those tiny flashes of light. And by working out where they were detected, they can work out the path of the neutrino. Now, the detector is not just useful for detecting neutrinos, it's also useful to detecting cosmic rays. And here we have a graphic showing you IceCube, as it says, the downward-looking telescope, because these neutrinos have passed through the Earth before coming out of the ground at the South Pole. But the detector is also useful for looking at cosmic rays. And as cosmic rays hit the atmosphere, they decay into particles called muons, which pass through the detector. So they've spent a long time working out exactly where these neutrinos are coming from. They come from all directions, of course, but a lot of them come straight through the Earth to the detector at the South Pole. And in actual fact, here's an example of a muon passing through the detector. As it passes through, you will see the blue lines. This is actual data, which represent the Cherenkov radiation that's given off. And this is a path of a muon, one of the shower that result when a cosmic ray decays in the upper atmosphere. And as you can see, they can work out exactly where it came from on the sky because of its path. So what is this all about, really? Well, what it's all about is the Milky Way. So here's our galaxy in optical. In optical light, that's what our galaxy looks like. You're probably familiar with something like that. If we look at it in radio waves, that's what the plane of our galaxy looks like in radio waves. This is what it looks like in high energy gamma rays. But now we can add to that. We can show you what the plane of the galaxy looks like in neutrinos. And it looks like that. So this is the first time that we've been able to map the plane of the galaxy using neutrinos. It's an immense achievement. There are lots of bright neutrino sources there. The next step will be to work out where those neutrinos are coming from. Neutrinos are created basically every time two atoms collide, it releases neutrinos. So this is typically in the hearts of stars, in thermonuclear reactions in stars. Neutrinos are also produced in supernovae explosions in large numbers. And basically, anytime two atoms collide, then they release neutrinos. Another way of looking at the same thing, just putting some more visible graphics on the galactic center and the galactic plane. As you can see, there are lots of neutrino sources there. So astronomers will now be trying to work out what is producing those neutrinos. So again, like the gravitational wave announcement, very, very big step forward for IceCube and neutrino science. Congratulations to both the Pulsar timing array and the IceCube team for two incredible announcements last week. And just to finish, I'd like to read this. It's a poem by, of all people, John Updike, who chose to write about neutrinos, and it's called Cosmic Gall. Neutrinos, they are very small. They have no charge and have no mass and do not interact at all. The Earth is just a silly ball to them through which they simply pass like dustmaids down a drafty hall or photons through a sheet of glass. They snub the most exquisite gas, ignore the most substantial wall, cold shoulder steel and sounding brass, insult the stallion in his stall, and, scorning barriers of class, infiltrate you and me like tall and painless guillotines. They fall down through our heads into the grass. At night they enter at Nepal and pierce the lover and his lass from underneath the bed. You call it wonderful, I call it crass. So there you are. So that's John Updike on neutrinos, and I think that's a wonderful poem. This is why I'm calling it Saturn's weirdest moons. Just give me 1 second, and here we go. Okay, hope you can see that. The first one is this moon, Hyperion, which is most bizarre. As you can see, it's got a surface that resembles a sponge, and Cassini flew by this close distance, about 5,000 miles away, and everybody was just amazed at what this moon actually looked like. Just a few details about Hyperion. It's 360 by 266 kilometers. Do forgive me if I slip between miles and kilometers, because I'm in that difficult age, you know. It's designated Saturn 7. In other words, it's the seventh moon from Saturn going outwards. It's actually 1.5 million kilometers away from Saturn. Its composition is mainly water ice with a bit of rock thrown in. And it's got an incredibly low density for a moon of its size. Now, what this means is when meteoroids, if you want to call them that, bits of rock hit it, instead of causing a big impact and a huge crater and flinging material into the space, the density of Hyperion is so low that it just sort of punctures the surface and digs downwards without actually making a huge crater. So as you can see from this image, if you look down the craters, they're cylindrical rather than sort of bowl-shaped. And this is put down to the low density of the material that allows any incoming rock just to go straight in. As I said, Cassini imaged Hyperion 3 times, the first in September 2005 and the last in May 2015. But Cassini's orbit did not allow it to approach Hyperion any more regularly than that. Only 3 times it managed to fly past the moon. There's a photo from another flyby of Hyperion. The bottom of the craters is a very dark reddish material, similar to the material that we find on some of the other moons like Iapetus, and that's why the crater bottoms appear dark. Complex organics are found in this material on some of the other moons. So it's to be assumed it's virtually the same here. And speaking of Iapetus, I mean, Iapetus is a weird body. Iapetus, those of you of a certain age may remember that in the book 2001: A Space Odyssey, it actually took place at Saturn rather than Jupiter in the book. In the film, it was Jupiter, but the special effects team couldn't come up with a realistic method in those days, back in the mid-60s, of representing Saturn's rings. So they moved the location of the final act of the film to Jupiter. But in the book, it was Saturn, and Iapetus is featured in the book because Arthur C. Clarke, who wrote the book, being a man of astronomy, he knew exactly what was odd about Iapetus, and what's been known for a very long time is that Iapetus is dark on one hemisphere, very dark, and very bright on the other hemisphere. And what Cassini found when it got there, as you can see in this image, is almost all of the way around the equator, there's this ridge. It looks like two halves of a moon have sort of been welded together, and that's the weld line. So this is certainly extremely odd. I'll talk about the ridge in a moment. So this was a very odd moon with its bright hemisphere and its dark hemisphere. It's 1492 by 1424 kilometers, so nearly spherical. It's designated Saturn 8. It's 3,560,000 odd kilometers from Saturn. Its composition, again, is mainly water ice with some rock thrown in. And that dark material is thought to have originated from outside Iapetus, perhaps from other moons. And the dark color is thought to be due to sublimation, which is a process where a solid turns from a solid straight into gas with no liquid phase. And that material is then further darkened by the action of sunlight. And it's not quite clear yet, I don't think, although I'm sure Lou or Bernard will correct me. I don't think there's any convincing explanation yet for why only one hemisphere is that dark color and the other hemisphere is covered in ice, which is why it's so bright. So that's Iapetus, but the ridge around the equator on Iapetus is amazing. It's 15 kilometers tall, and if you compare that with Everest's 9 kilometers, so it's getting on for twice the height of Everest, that ridge you see before you. It's thought to be formed from the debris of a ring that Iapetus once had that actually collapsed onto the planet, forming this ridge around the equator. Although I don't think that's settled yet, but I think that's the leading theory, that it's the remains of a ring that collapsed onto the surface, onto the equator of Iapetus. This is an amazing image, but this image I absolutely adore, which is a close-up of that ridge. And I did feature this as one of my favorite space images when it was my turn, because this is such a beautiful, haunting image. And you can imagine exploring that amazing terrain. It's just absolutely stunning. So that's Iapetus. Now we move on to a truly weird moon of Saturn, and this is the moon Pan. Now there are two images of it here taken by Cassini from different angles. It's been called the ravioli moon because it looks like a piece of ravioli. How on earth did a moon like this form and get that, again, a thin ridge right around its equator? It looks like some sort of a UFO. This moon is very small compared to the others. It's only 35 by 25 kilometers. It's designated Saturn XV111, and it's 133,000 kilometers from the planet. Its composition, although it's uncertain, it hasn't been directly measured. It's presumed to be mainly water ice, again, with some rock thrown in. And Pan is what we call a shepherd moon of Saturn. And a shepherd moon is one that literally confines one of Saturn's rings and keeps it as a ring so that it doesn't dissipate and spread out. And in this case, what Pan does is to keep the Encke gap, which is a gap between Saturn's rings, free of material. So it's sweeping up material from the Encke gap all the time. And it's this material that it's swept up, which is thought to fall on its surface and form this equatorial ring over time, over a long time. So it's literally because the moon is acting as a sort of hoover, if you like. It's hoovering up this material, which settles on its equator and forms this this incredible ridge around it. Now, just so you know where we are, these are Saturn's rings, and you can see towards the right, there's the Encke gap. So we've got several gaps in Saturn's rings. We've got the Huygens gap. We've got the famous Cassini division, which was first seen by Galileo. We've got the Encke gap, and we've got the smaller Keeler gap. And Pan actually patrols, if you like, within the Encke gap, sweeping up any material that has entered it from the rings. And here's an image taken by Cassini of Pan actually in the Encke gap. So that's a beautiful image of that little moon actually in the middle of the Encke gap there, which I think is an amazing image. We move on now to our last moon of this evening, Atlas. Now, Atlas is another moon that similarly has a ridge around it. This, I think, is an amazing image because basically you're seeing a mountain on the top of the moon with this weird ridge around its equator. And Atlas is, getting on for the same size as Pan, 40 by 35 by 18.6 kilometers. It's designated Saturn XV. It's 137,000 kilometers from the planet. Again, it's thought mainly to be water ice. And because for a long time, Atlas was thought to be shepherding the A ring to make it keep its shape, if you like, it's now thought that it isn't actually a shepherd ring of the A ring at all. And latest information indicates that the ring is kept in its within its limits, if you like, by the action of three other moons, Prometheus, Janus, and another one I can't remember. So Atlas is not actually a shepherd moon. But in that case, how did it get that? If it's not picking up material like a shepherd moon does, how does it actually get that ridge around its equator? Well, something that Cassini discovered in 2004 was this ring of material that is actually within the orbit of Atlas. And this is the material that Atlas has swept up and has formed that ridge around its equator. That answers the question. So there you are. So they're the tonight's moons, the weirdest moons of Saturn. And I think you'll agree in terms of what they look like. They're certainly extremely weird moons. So there you are.
Yeah, they certainly are. Yeah. And was there ever, when you mentioned the last group, the three, you said, what was it? You said Prometheus, Epimeth. Was there ever one Pandora?
Could be Pandora. Yes, it could be. Have to look that up.
Yeah, I could be wrong there. They're just all I spread. But you were talking about Hyperion. Of course, Hyperion, as well as looking strange, it's got a very strange behaviour as well. It's tumbling totally out of control.
Yes, it is.
There's nothing unified.
No.
Yeah, nothing unified about its the way it rotates, or it's literally tumbling, and you can't predict anything. Yeah. It keeps changing all the time. Yeah, and as you said, it's a very strange sponge-looking looking thing. But also, I mean, as we know, Saturn's got loads of moons or moonlets, and of course, some of the naming's quite novel. I'll just read you this. Saturn has two orbital groups of prograde irregular satellites. The individuals in one are given Inuit names such as Sironwak, and in other Gaelic names as Alborix. Each group could be remains of a larger moon destroyed by collision. Apart from Phoebe, Saturn's retrograde irregular satellites have Norse names and include groupings that could each represent fragments of the same captured asteroid. So, yeah, they've got so many, with Jupiter and Saturn having so many moons, they're really having to
spread the net to find names for all these things.
Names for them.
And of course, most of them are found by that group of people sat on the Hawaiian mountain, and all they do all day is look for moons, and they're quite successful at it. So, as we said, they need to get a proper job.
Nice work if you can get it, Daz. That's all I want to say.
Yeah, too right.
Bernard or Lou, do you want to add anything about any of those moons?
I'll let Lou start.
Well, the only thing I was thinking is that this chaotic tumbling of Hyperion seems to be a product of its both its irregular shape and its 4-3 resonance with Titan. So these two qualities act together to give it this kind of strange rotation movement.
Yeah. Thanks.
With regards to Iapetus, you were wondering about the difference in one side is brighter and the other side is darker. Isn't that related to the trailing side and the leading side, where the leading side just picks up all the dust and everything as it goes through Saturn, as it orbits around Saturn?
I believe that's correct, Bernard.
Right. So,
Steve's just popped in the chat. Steve's just popped in the chat probably a theory about that. So if you look at the curved horizon of Iapetus on one side of the ridge and trace it across, it doesn't seem to match the circle on the other side of the ridge, suggesting a compression feature. Maybe.
Interesting.
So you've two things pushing together. So
if that's the case, if it is a case of the leading edge and the trailing edge, or the trailing side, is Iapetus tidally locked?
You're the one who did this presentation. You should know. I forgot.
I've forgotten as well. Yeah.
Too many moons around Saturn.
Most moons are, but I don't know about. I don't know about Iapetus in particular.
Yeah, I'll have to ask ChatGPT about that. Okay, so there we are. So those are the moons of the week. We'll start by having a look at the actual topology of the lunar South Pole. And this is a beautiful image of the lunar South Pole taken by the Lunar Reconnaissance Orbiter. Extremely haunting, really weird landscape. But let's talk about it. So this is the topology of the moon, basically. We've got the near side and we've got the far side. The South Pole is characterized by huge craters, very deep ones, with ridges between their rims, and just on the far side of the moon, and therefore invisible most of the time from us, is this big blotch here called the Aitken Basin, which is either one of or it's the biggest impact site in the solar system, a massive impact on the moon. And we get to see a little bit of it when occasionally when we can see a little bit of the far side of the moon. But as you can see, the near side characterized by a lot of craters and quite mountainous terrain. Now, the actual lunar South Pole is in a very not obvious position. This is looking at the area of the lunar South Pole. And the lunar South Pole is actually exactly here on the rim of a crater called Shackleton, named after Ernest Shackleton, of course, the famous British explorer. And the lunar South Pole is exactly there, literally on the rim of the crater. And the Shackleton crater is 21 kilometers wide by 4.7 kilometers deep. But we've got some bigger ones around it. We've got Hayworth, for example, 51 kilometers, its depth unknown. We've got Shoemaker, named after, of course, the famous scientist Eugene Shoemaker, and 50 kilometers wide by 2.5 kilometers deep. Faustini, 39 kilometers wide, depth unknown. De Gerlache, 32 kilometers wide and depth unknown. So you've got some pretty wide craters here, and some very deep ones. And you can see the ridges here between the craters, and making the whole landscape look really sort of mountainous and big. Now, interestingly, a lot of these craters are in permanent shadow. The sunlight never penetrates them, never illuminates them.
I'm Ernie Wright, I work in the Scientific Visualization Studio at NASA's Goddard Space Flight Center. We're looking at a computer model of the view at the south pole of the moon. This is like a time lapse to show the motion of the sun and the Earth and how the shadows change over time. Things don't rise and set in the usual way here. The sun travels around the horizon, never getting more than 1.5 degrees above or below it, so there are always these long shadows. And from here, the Earth appears to be upside down and rotating backwards, but that's just because of our point of view. The Earth doesn't move much in the moon's sky. It's always in roughly the same place, just sort of bobbing around. That's true everywhere on the near side of the moon. It's a consequence of the moon always pointing the same face toward Earth. It takes about a month for the sun to make a complete circuit around the horizon, and every so often, it'll pass behind the Earth, creating an eclipse. I've slowed down time here a little so that it's easier to see. On Earth, that would be a total lunar eclipse, the moon passing through the shadow cast by the Earth. But if you're standing on the moon, it's an eclipse of the sun. The terrain at the South Pole is especially rugged. The rim of Shackleton craters in the foreground here, and the mountain off on the horizon, unofficially known as Mons Malapert. It's about 85 miles away. Shackleton crater is about 13 miles wide. Not quite as wide as the Grand Canyon, but it's twice as deep. Sunlight never reaches the crater floor, so temperatures there are around 300 degrees below 0 Fahrenheit. This model of the terrain is made possible by Lunar Reconnaissance Orbiter, which has been mapping the surface of the moon from lunar orbit since 2009. LRO's maps will be incredibly important for exploring the moon and locating water and other resources there.
That's the topology of the south pole of the moon. Imagine these craters never having seen sunlight in billions of years. And this brings us to the topic of, believe it or not, water, because a lot of water has been discovered, not just at the south pole, but at the north pole of the moon as well. Now, these are just some of the spacecraft that have detected it. Lunar Prospector, I think, was the first in 1998, and it detected a possible 300 million tons of water at each pole, so 600 million in total. Then we got Clementine in 1994, detected water at both poles. Chandrayaan-1, the predecessor of Chandrayaan-3, which is hopefully going to land on the moon on Wednesday, was an impactor mission to slam an impactor into the moon, and it detected water ice near Shackleton crater. The LCROSS mission from NASA, again another impactor, detected water ice near Cabeus crater, another crater at the south pole of the moon. The Deep Impact mission, you may remember, to NASA's wonderful mission to ram a probe or an impactor into an asteroid, and that was in 2009. But on its way to the asteroid, it bypassed the moon, and it actually detected water vapor in the moon's atmosphere. And if you're going to turn around and say that the moon hasn't got an atmosphere, well, yes, it has. It's just a very, very thin one. But the Deep Impact mission detected water vapor in that atmosphere. And Chang'e 5, you may remember, I think I reported on this a couple of weeks ago, that around impact sites on the moon, around craters, in other words, it found all these glass beads laying about on the surface that were full of water. So there may be a huge amount of water locked up in those glass beads around craters just on the surface of the moon. So these were all momentous discoveries. Now, the NASA flying observatories, SOFIA, which, as you may know, was in a modified 747, an infrared telescope, looked at the south pole of the moon, and this is what it saw. And you can see here that this is basically telling us that this is water, and lots of it at the lunar south pole. So this is all very exciting. Now, if you can get at that water, well, what does it do for you? What would you use it for? Well, astronauts would use it for all sorts of things, but they would use it obviously to survive, for life support. They would use it for hydroponics, to grow plants on the moon. And they would use it for rocket fuel, because you can split the water into oxygen and hydrogen and make rocket fuel out of it. And of course, they would use it for research, general research about the moon. But there would be other things, I'm sure, that people will think of as well. So it's very, very interesting. Where does the moon's water come from? Well, a few possible places. Comets and asteroids is obviously one, but the solar wind is another, because the charged particles from the sun interact with the lunar surface and can create water molecules, believe it or not. And it can also be from the Earth itself, because don't forget, we believe that the moon was formed after a Mars-sized body collided with the Earth early in its history, and a huge amount of the Earth's crust was thrown into space and then coalesced quite quickly, as it turns out, to form the moon. Well, the water could have come from the Earth in that way. We don't know, basically, is the answer. But then again, we don't really know where Earth's water came from in the first place. So there we are. So that's a bit uncertain at the moment. So a few possible origins for that water from the moon, but I think a lot of it primarily will come from comets and asteroids. Now, how do we get there? Well, actually, as Luna 25 found out this week, landing on the moon's south pole, or the north pole, come to that, is not easy. But actually landing on the moon generally is not easy. 50% of all attempted landings on the moon have failed, and you may know that that's exactly the same failure rate as Mars, funnily enough, in a weird cosmic coincidence. So what you have to do, you have to put your spacecraft into a normal, inverted commas, orbit around the moon, a non-polar orbit, and then over time slowly change its orbit so that it becomes a polar orbit. Sounds easy, but actually it's quite complicated. And the loss of Luna 25 appears to have occurred during this crucial phase of changing the orbit into a polar orbit, ready for landing. We don't know exactly, but it looks like that's what happened. So it's not easy. But if everything goes well, this is the place on the moon in late 2025 where NASA will land. And it's been chosen in close proximity to Shackleton crater, which, as we saw, has got lots of water in it. So hopefully astronauts will descend on SpaceX's lunar Starship towards the moon's south pole and land on this sort of mountainous region here, which is called Malapert Massif. It's thought to be actually part of the rim of the Aitken Basin, that massive impact crater basin that is mainly on the far side of the moon. But the Malapert Massif is thought to be part of it. And hopefully in 2025, this is where NASA will land. Assuming that everything goes well, they want to get at the water. So how do we actually extract ice and water from the moon? Well, you've got a number of different options for getting it out. You can scoop it with a robotic arm, but it turns out that's not very efficient and certainly not energy efficient. You can use a laser to vaporize the ice and then collect the water vapor. That, I think, would be a little bit tricky to do, but it's one option. You could use a heat exchanger to just melt the ice and collect the liquid water. And there are other methods they're looking at, including just straight drilling, something called electrodialysis, and heating the ground with microwaves to release the water held up in it. But there are lots of people working on this. So by the time that humans are ready to start mining the ice on the moon, then hopefully we'll have a good method of doing so. And lastly, talking about the race to the South Pole, well, we've got all sorts of countries involved in this. India, of course, Chandrayaan-3 is going to land on Wednesday, all being well. Fingers crossed. Hope it goes well, India, because God knows you need a success. They're also looking forward to the future, to Chandrayaan-8. I don't know why the numbering has changed so much, but it's scheduled to launch in 2025. And like Chandrayaan-3, it will consist of an orbiter and a lander and a rover. And they're going to conduct a detailed study of the lunar South Pole, including the search for water, ice, and other resources. The USA has got the Artemis project, and it's all mapped out. Artemis 2, an uncrewed mission to fly round the moon, much like Apollo 8 did in the days of Apollo in 1968. Artemis 3 will be the first mission to actually land people on the moon, the first woman and the first person of color. Artemis 4 is going to deliver the Lunar Gateway. This is a space station that's going to orbit the moon and be used as a staging post for future Artemis missions. Artemis 5, that's going to launch in 2027, and they're going to stay on the moon for a much longer period to carry out experiments and collect more samples. Then we've got Artemis 6 in 2028, delivering a habitat module to the Gateway. Artemis 7 launching in 2029, where the astronauts will stay on the moon for even longer to do valuable scientific work and collect and analyze more samples. China has got the Chang'e 7 mission scheduled to launch in 2026, consisting of an orbiter, lander and rover, and a small flying detector. Not quite sure what it's going to be detecting, but I suspect it's ice. And again, it's exploring the lunar South Pole for evidence of water ice and other resources. Chang'e 8 in 2028. This is going to actually try to extract water from the lunar surface using what's called, and it's a whole acronym, ISRU, which stands for In Situ Resource Utilization. Why can't they just say mining, for God's sake? Because that's what it is. Chang'e 9 in 2030, and they're going to land astronauts. China's going to land astronauts on the moon near the lunar South Pole. And beyond 2030, China is in partnership with Russia to develop the International Lunar Research Station, a permanent base at the South Pole of the moon. And actually, there are quite a few Western companies already helping China get this thing ready. So it's definitely a goer, although Russia's role in it is a bit in question now, especially after the Luna 25 loss this week. So we'll have to see what happens there. And of course, we'll keep you posted. Others, Japan is planning to launch a mission to the lunar South Pole in the 2020s. It's called SLIM. This is a much nicer acronym, Smart Lander for Investigating the Moon, which I like. That's short and sweet and to the point. South Korea are planning to launch a mission to the lunar South Pole in the 2030s. That's a little more of an unpronounceable acronym. It's KPLO, the Korea Pathfinder Lunar Orbiter. UAE, the United Arab Emirates, is planning to launch a mission to the lunar South Pole in the 2020s. That's called Hope Probe, because their Martian mission is also called Hope, of course. India and Japan have a plan to develop a mission called the Lunar Polar Exploration to explore the poles on the far side that we can't see directly from the Earth, launching before 2026. So that's a nice international collaboration. Just a word about legalities of all this. The Outer Space Treaty, signed by all sparing nations in 1967, specifically says outer space, including the moon and other celestial bodies, is not subject to national appropriation by claim of sovereignty, by means of use or occupation, or by any other means. Basically, it means no country can claim all or part of the moon, that it's there for the benefit of all humans. So China, for example, couldn't set up a lunar base and then claim territory on the moon. This has never, as Daz and I were saying earlier, this has never really been tested. It's still in force, the Outer Space Treaty, but whether it would actually work in a court of law now, or we don't know what would happen. Hello, I'm Andy from Space Oddities. Next to black holes, neutron stars are probably the most bizarre objects in the universe. First predicted in 1934 by astronomers Walter Baade and Fritz Zwicky, it was not until 1967 that they were first actually observed by Jocelyn Bell, now Dame Jocelyn Bell Burnell, then a research student at the University of Cambridge. In these Weird Wonders videos, we're going to enter the weird, wonderful world of neutron stars, where matter, magnetism and gravity behave in ways we can scarcely comprehend. In this first episode of the series, I'll be looking at how neutron stars form. Go out under a starry sky in winter or early spring, and you cannot fail to notice the constellation of Orion, one of the most recognisable in the heavens. At Orion's left shoulder there is a bright star with an obvious orange colour. This is Betelgeuse, a red supergiant star some 600 light years away. Betelgeuse is a truly gigantic star, shown here compared in size to some other giant stars and our Sun, which, as you can see, is tiny by comparison. Betelgeuse is so vast in size that, despite its distance, astronomers have been able to capture an image of its surface, which is not possible with more than just a few stars. Most stars, even in the largest telescopes, appear as mere points of light. The red giant phase of a star occurs when it nears the end of its life, starts to run out of hydrogen and puffs up into something monstrous and bloated. This is in fact the fate of our Sun. In 4 or 5 billion years' time, the Sun will be nearing the end of its life and will have expanded to become a red giant star, swallowing Mercury, Venus and very possibly the Earth as well. This picture shows what the Sun may look like from the surface of the Earth when our star becomes a red giant. After millions of years as a red giant, radiation pressure from the core of the Sun will cease and our star will shrink to become a slowly cooling white dwarf star, finally ending its life a cold, dark cinder. But what of stars larger than the Sun? What happens to them? Stars with more than about 8 times the mass of the Sun do not become white dwarfs. Instead, they end the red giant stage of their lives by blowing themselves apart in what's called a Type II supernova explosion, a detonation of such unimaginable magnitude that in just a few seconds the dying star may release more energy than our Sun will emit during its entire 10 billion year life. In this type of supernova, the star blows away its outer layers, leaving just the core of the star behind. Immediately after the supernova explosion, there is no longer any outward radiation pressure from the core of the star. Consequently, in the sudden absence of any resistance, gravity is able to suddenly and violently compress the core, reducing its size from thousands of miles in diameter to just a mere handful of miles across. This process may happen within a few seconds. The atoms in the core are squeezed closer and closer together, so much so that electrons orbiting the atoms are unable to sustain their orbits and crash inwards to the atomic nucleus, combining with the protons to form neutrons as a bizarre ultra-dense element called neutronium. A neutron star is born, which consists largely of neutronium. It possesses between 1 and 3 times the mass of the Sun, packed into a sphere perhaps just 10 miles across. You may be familiar with the periodic table of elements, where each element has an atomic number representing the number of protons present in its nucleus. Hydrogen, for example, is atomic number 1 as it has just 1 proton. Neutronium is numbered 0 in the periodic table because it does not have any protons. They have all been converted to neutrons. At this point, gravity cannot compress the new neutron star any further, as something called neutron degeneracy pressure pushes back against gravity, preventing the neutron star from shrinking further under gravity's relentless assault. The neutron star is now in finely balanced equilibrium. However, if the star was originally 5 times or more the mass of the Sun, not even neutron degeneracy pressure can exert sufficient force to stop collapse of the core altogether. Gravity wins the battle by compressing the core to a mere point, and a black hole is born. Therefore, whether the result of a supernova explosion is a neutron star or a black hole depends purely on the mass of the star. Neutron stars are bizarre objects indeed. Here is one shown for size comparison with Manhattan. Because up to 3 times the mass of the Sun is packed inside this small sphere, its density is almost incomprehensible. 1 teaspoonful of neutronium would weigh 4 billion tons. Because of its huge mass packed into a small area, the gravitational field of a neutron star is perhaps 1,000 billion times stronger than the Earth's. This intense gravity means nothing taller than a millimetre or so can exist on the surface of a neutron star. Anything taller would be immediately crushed by gravity. A neutron star is therefore a perfect sphere. Astronomers sometimes observe violent radiation outbursts on neutron stars which are thought to be starquakes, where the surface might slip by a couple of millimetres. This is enough to generate huge amounts of energy. The incredible gravity also means that if you were to drop a ball from a height of 1 metre onto the surface of an average 12-kilometre diameter neutron star, by the time the ball hits the surface, it will be travelling at 1.4 million metres per second, or 3.1 million miles per hour. And what of the interior of the neutron star? It must be said that astrophysicists are unsure about what exactly a neutron star looks like on the inside. As we cannot crack one open, we have to be guided by the physics alone, which suggests that the interior is made up of extremely exotic materials which do not exist on the Earth and which cannot be reproduced in a laboratory because of the extreme pressures and forces present. Here's a diagram from NASA showing the possible composition of a neutron star, but we cannot test this model through observations. The starquakes I mentioned earlier might give us an idea in the future of what's going on inside a neutron star, but short of travelling to one and making close-up observations, there's no way to investigate what these bizarre beasts in the cosmic zoo are hiding beneath their surfaces. As the closest neutron star is 170 light years away, or 1020 trillion miles, we won't be travelling to it in the foreseeable future. Well, that's it for the first part in this series of videos about neutron stars. Next time I'll be looking at pulsars, those rapidly rotating neutron stars which fire huge beams of radio energy from their poles like a celestial lighthouse. I do hope you enjoyed this video, and if you have any questions or observations, please don't hesitate to post them in the comments. We hope you can join us, the Space Oddities, on Mondays here on this channel at 8 PM UK time for astronomy news, chat and discussion from our resident panel of experts. We also hope that you'll subscribe to our channel, like our videos and tell all your friends, co-workers and families about us. Well, from me, Andy, until next time, goodbye.